Hey, let's talk a little bit more about sound. Your assignment for this video is to just take some notes and then attach those notes into Google Classroom. So please make sure you have a notebook out and that you're writing a few of these things down. These will also be things that you can use when it comes time to do your final assignment for this week, which is a Edpuzzle that will be counted as a quiz. So that'll be useful for that as well. We're going to start by talking about something called resonance. So imagine yourself at a park with a little kid and they're swinging. You can't just randomly push whenever you want to push. You have to find when the swing comes back, you have to push with the swing. So that's kind of the concept of resonance. Resonance is because all objects have a natural frequency that they will vibrate at. So your kid swinging in this analogy has their natural swinging frequency. If something nearby vibrates at that same frequency, i.e. you pushing the kid on the swing, if you're doing it at the right frequency, if you're doing it when the kid comes back, you're going to make the kid vibrate even more or move even higher, by pushing their swing, which is what your goal is. And so we can have that happen in a number of situations. You've heard of, glass breaking when someone sings or, those kinds of things. That's all because of resonance. So, you might have a cup and you fill the cup up with a certain amount of water, and then you take your finger and you go around the top of it, and that might cause the cup to resonate. It makes the air inside the cup, depending on how much water you have, will vibrate at that same frequency, and you'll get a tone. A couple other examples I want to show you this video of a tuning fork causing resonance with another tuning fork. So a tuning fork looks like this, and it's just metal, and when we hit the tuning fork, which we will do here, that vibration causes the air to vibrate. The air vibrating went into the microphone and caused us to hear that tone. And you just kind of saw what he had to do is he stopped one, he had to stop the other. So both of those tuning forks are the same. The one he hit is clearly making a tone. But not only is the one he hit making a tone, but the one he never touched made a tone as well because it was resonating. The air moving from the initial tuning fork caused the other one to move as well because it was at its natural frequency. Now he's going to add a weight to it. That will change the resonant frequency. It will change the way that tuning fork naturally resonates. Now this one is still making its tone because we touched it. But there's no tone from the other one because it was changed by what was done there. So that's resonance and kind of helps you see that. Another example of resonance in nature is the Tacoma Bridge collapse that happened, and I'll let you hear the story of that right from the video.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
And a dog. So sad, so sad. And a dog. So that's resonance, and the Tacoma Narrows Bridge is an example of a bridge that was built without thinking of resonance, and when the air blew through, it was vibrating that narrow space, kind of a canyon, at the right frequency for that bridge. The bridge then started vibrating and vibrated way more than it wasn't because of the wind, it was because it just had the right frequency and caused it to vibrate to pieces. So that's resonance. Not really a wave interaction like the four that we talked about before, but kind of a concept that's specific to sound. So we talked about 4 wave interactions last week. Those interactions were reflection, refraction, diffraction, and interference. Refraction's not really an issue per se when we're talking about sound, so it doesn't have a lot of really obvious effects. So we're not going to talk about that one. But basically, reflection, when you have reflection of sound, you hear an echo. Diffraction is how you could hear your mom and dad talking in the next room or something like that. And then interference, we'll talk about beat patterns, and I'll show you what that looks like. So let's start by talking about reflection. Reflection, you could be in a big open space and you could easily hear, kind of if you're maybe in a canyon, it always happens every time I'm talking. When I'm talking right now, my sound waves are reflecting. But when we're working with multiple surfaces, the waves will reflect in different ways, and we don't hear them as a single sound or an echo. It's when it has a really hard, large surface that you're near with not much in between to absorb any of the sound that you're going to hear a pretty significant echo. And we can use things like echolocation. Dolphins use that. They send out sonar waves, which is a kind of sound wave. And when it comes back, they sense it. And then they can, by knowing how fast it went and came, they can figure out how far away something is. So it's a useful thing, and we use it for ships and things like that, as it shows in the picture. Diffraction is just like it sounds like. So we talked and saw the video last week of diffraction happening around a barrier in a pool, but the same thing happens with sound. So the original waves that go out don't just go out in one direction. So if we had no diffraction, we would have only somebody standing right here could hear this sound. Somebody over here wouldn't hear it, because if there was no diffraction, it would only go in that one way. But the reality is sound waves bend around small corners or small openings and corners. And so therefore I can be standing over here. The speaker could be on the other side of the wall, and I can still hear what they're saying. It's good for eavesdropping, right? Okay, so then we're going to go back to interference, and you can read a little bit more about interference. You have the option to do a couple of different projects this week, and one of them is interference comes into play when we're talking about, no, you know what, that's not what I want to do. Interference comes into play when we're talking about things like the acoustics in a large room, dead spots and things like that. So you could become an acoustical engineer, where you could actually be on a team of people that designs large stadiums or rehearsal places, or just lots of different things, because we want to make sure that in large auditoriums and things like that, that there's good acoustics there. So physicists are on the teams to build and design those kinds of buildings, and you could do the same thing. So let's go ahead, and I want to show you something. Oh, not that, sorry. By dog and car. Let's come back to this video. So what he's going to show you here is how if we play 2 tones, they can interfere, and they can constructively and destructively interfere. So he's going to play our original tone. And do you hear that kind of wah, 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 that kind of, where you hear the louder part, that's constructive interference, and where you hear the lesser part, that's destructive interference. And we can actually do, you can actually count however many beats you hear. The number of beats that you hear is directly related to the number of hertz different between the 2 sounds. So if you're off by a certain amount, you can know that. So let's see if I can show you that. Sorry, I didn't have this one up and ready to go, but I think I can get it for you. So you could check this out if you want to, but what we can do is we can set this to play some different tones, and when those tones are playing, let's see if I can get them to play. Turn the sound on. Okay, so if they're playing exactly the same, I don't know if this is going to be loud enough for you guys to hear, but if they're playing the exact same tone, we don't hear any difference. They're exactly the same, and you can see that the 2 waves are kind of adding up. So we've got the the peak of one and the trough of the next is lined up perfectly. But if we move them off just a little bit, we'll see that when we put the waves on top of each other, and you can barely see it, but they're just not quite on top of each other here, and then they line back up here, and then they separate back over there, and so on and so forth. Let's zoom in a little bit so we can see that. And if you can listen, I'm not sure if you can hear it. But you can hear the beats, and they're off one every second because they're off by 1 hertz from each other. So if we make them go off by 2 hertz, you hear 2 beats per second. If we make them off by 3 hertz, you hear 3 beats per second. And so on and so forth. And you can start to see, as we're getting off by more, you can start to see over here where they're starting to really cause a bit of a interference pattern with each other. And you can see when we zoom way out, here's the loud part of the beat, here's the quiet part of the beat where they're interfering more. And the further we get off from each other, we start to get these wonky patterns, and we get these strange interference patterns where now we are having high and low interference patterns kind of with each other. So that's what interference is in terms of beats. So let me get us out of that, and then we'll finish up what we're talking about in terms of sound. So let's do a quick summary of sound and what we know about it. In some Western movies, a character would be shown putting an ear to the hard ground to find out if someone was coming. Does this work? Why or why not? So think about how we learn sound moves and what it moves quickly in and what it moves slowly in, and include at the end of your notes the answer to this question. Would you be able to hear someone coming further away if you put your ear down to the hard ground? And then the second question, if you're in a space station and someone tells you that the sensors have detected an explosion, how long will it be before you hear that explosion? Again, what have we learned about sound, and what do you know about how long it would take for you to hear an explosion at a space station that you are on? So add those as the last 2 things in your notes, and then go ahead and submit them in Google Classroom, and have an awesome day. I will see you in class or in office hours, and be praying for you till then. Bye.